Hey guys, this is Jacob Hur, and today I'm going to be talking about continuity and one-sided limits. So let's start by saying we have a function of f. For this function to be continuous at x equals c, there must be no holes, no jumps, or gaps on the graphs at c. A function can only be continuous if these three conditions are met at that point. In this case, the function is f and the point is at x equals c. So the first condition that needs to be met is f of c must be defined. If a function does not have a defined f of c, then that function cannot be continuous. The second condition is that the limit as x approaches c of f of x must exist. Even if that function has a defined f of c, if the limit as x approaches c of f of x does not exist, then it still cannot be continuous. Finally, the third condition is that the limit as x approaches c of f of x must equal f of c. So even if the past two conditions are met, if they don't equal each other, then they cannot be continuous. Let's move on to some examples. In this graph over here, you can see that f of c is not defined because of the empty circle over here. This means that this graph cannot be continuous. On the second graph over here, f of c is defined because of that filled circle right there. However, the limit as x approaches c of f of x does not exist, which means this graph still cannot be continuous. This third graph over here does have a defined f of c, and the limit as x approaches c of f of x does exist. However, they do not equal each other, which means this graph cannot be continuous. However, in this graph, as you can see here, f of c is defined. The limit as x approaches c of f of x does exist, and they do both equal each other, which means this graph is continuous. To further learn about continuity, we also need to learn about discontinuity. Let's say that we have an open interval a to b which contains a real number c. If a function of f is defined everywhere on that interval, maybe not at c, and f is not continuous at c, then f is said to have a discontinuity at c. There's actually two types of discontinuities. There's the removable type and the non-removable type. I'll go over the removable ones first. If f can be made continuous by appropriately defining or redefining f of c, then the discontinuity at c is called a removable discontinuity. To make it easier to understand, I have some examples. So as you can see here, it's the same graph as what we saw before on the past slide. However, by adding f of c or defining f of c in this graph, we can make this graph continuous, which means this graph contains a removable discontinuity. On this graph, we do already have a defined f of c. However, we can redefine that to make this graph continuous, which means this graph also has a removable discontinuity. Now to talk about the non-removable ones, if f cannot be made continuous by appropriately defining or redefining f of c, then the discontinuity at c is called a non-removable discontinuity. For example, in this graph, no matter if you define or redefine f of c, you cannot make this graph continuous. And hence, because of that, this graph contains a non-removable discontinuity. Let's move on. So let's try some of these examples. So first, we have a function of f of x equals 1 over x. And as you can see, I already graphed this over here. As from this graph, you can see that as this part of the graph approaches 0, it travels to infinity. And as you go back from, as this part of the graph approaches 0, it goes to infinity, which means because the limit as x approaches 0 of f of x does not exist, this function has a non-removable discontinuity at x equals 0, and this function is not continuous. if you go to the second example, we have h of x equals x plus 1 when x is less than or equal to 0, and x squared plus 1 when x is more than 0. And I graphed that over here already. And as you can see, because this function of h has all the three conditions met to be continuous for the entire graph, this graph here is continuous because there are no hops, jumps, or holes in this graph at all. To do more examples, I have a few more examples over here, and this time we actually need to graph the functions in order to solve them. So let's graph this one. So first we have g of x equals x squared minus 1 over x minus 1, which you can be graphed with here and like that. This graph is because of this hole over here and f of c not being defined, this graph cannot be continuous. However, this graph contains a removable discontinuity, meaning if you were to define this point, then this graph could become continuous. And for this graph, we have y equals sine of x. And to graph that, we put here and here. So the graph would look like that. Since this graph does have all the values being defined and fits all three of the conditions we talked about before, this graph is continuous. Now let's talk about one-sided limits. Like how the name indicates, one-sided limits are limits taken either to the right or to the left of a point. A limit from the right means that x will approach c from the values greater than c and is indicated by the small plus sign. And as you can see here, the limit as x approaches c of that little plus sign of f of x, that means it's from the right. A limit from the left means that x will approach c from values less than c and is indicated by the small negative sign. So as you can see here, the limit as x approaches c with the little negative sign of f of x means that it's from the left. Let's try an example. So it says here that we need to find the limit as x approaches c from the right of f of x. So we follow from the right, and we end up right here, which is at 1. So this will be 1. And the second question is the limit as x approaches c from the left of f of x. We follow from the left, and we end up here, which is at 5. And to answer this question, is the function continuous at c? Well, in this case, c is at 4, and since the limit as x approaches c of f of x does not exist, this cannot be continuous, so no. If not, what kind of discontinuity does this contain? Removable or non-removable? Since you can't define f of c to make this graph continuous, this contains a non-removable discontinuity. Now that you guys know what one-sided limits are, let's look at a theorem. This is the existence of a limit theorem. Let f be a function and let c and l be real numbers. The limit of f of x as x approaches c is L if and only if the limit of x approaches c from the left of f of x equals L and the limit as x approaches c from the right of f of x equals L. Since that kind of sounded really complicated, let me try to simplify it a little bit. So this means that if a function of f is real valued, then the limit of f at c is L, if and only if both the right-handed and left-handed limit of f at c exists and are equal to L. So to see an example here, f of c already exists and it equals 5 over here. And if you follow the graph for the limit of x as x approaches c from the left, you can see that you meet over here, and that's also 5, so that's 5. And as the limit as x approaches c from the right of f of x, so you follow here, and that's also 5. Since all three of them are 5, f of c exists, and both sided limits equal 5. This means that the limit as x approaches c of f of x equals 5. Now, these are some questions that I want you guys to try on your own. I'll put this on for a little bit. And good luck.